Okay, good morning, class. Today we're going to take a look at limits at infinity. Yesterday, we dealt with infinite limits. Today, it's going to be limits at infinity. So, we can state if the limit as x goes to positive or negative infinity of f of x is equal to L, then y equals L is a horizontal asymptote. Okay, so if you take the limit and you end up with a number divided by 0, then that limit is going to be positive or negative infinity. Okay. If, on the other hand, you take the limit and you end up with a number divided by positive or negative infinity, then that answer is 0. So if you think about it, let's say you have 1 over 10, 1 over 100, 1 over 1,000. As your denominator is growing and growing and growing, that number is getting smaller and smaller and smaller. And eventually, it's going to converge to 0. And then finally, the limit as x goes to positive or negative infinity of 1 over x to the r is equal to 0. So as x goes to positive or negative infinity, you're still going to get 1 over infinity, which is 0. Okay. So let's take it back to a little bit of pre-calculus. Let's say you have r of x is equal to p of x divided by q of x. And let's say you have some a sub n x to the n, so an nth degree polynomial in the numerator. So that's plus some a sub n minus 1, x to the n minus 1, plus a sub n minus 2, x to the n minus 2. Okay. Divided by where q of n, or q of x, is equal to some b sub m x to the m plus b sub n minus 1 x to the m minus 1 b sub m minus 2 x to the m minus 2. Alright, so what did we learn about this in pre-calculus? Okay. And then how are we going to relate that to calculus? So if n is equal to m, so the degree of your numerator is exactly the same as the degree of your denominator, then your horizontal asymptote is y is equal to the coefficients a sub n over b sub m. If n is less than m, so in other words, the degree of your polynomial, the degree of the numerator is smaller than the degree of the denominator, then your horizontal asymptote is y equals 0. So let's think about that. So let's say you had x squared, let's say you have f of x is equal to x squared over x cubed. Okay? And you're taking the limit of that as x goes to infinity. Because remember, we already said before that the limit as x goes to infinity of f of x equals L, then that's your horizontal asymptote. So as x goes to positive infinity or negative infinity, the limit will give you your horizontal asymptote. So in this case, well, this is the same thing as, well, x squared divided by x cubed would be 2 over x. And think about the limit as x goes to infinity of 2 over x. You're going to get 2 over infinity, which is 0. So in this case, your horizontal asymptote would be 0. Okay, number 3. If, on the other hand, n is greater than m, then you have no horizontal asymptote. So again, x cubed over 2x squared, well, if we simplify that, we end up with x over 2, and the limit as x goes to infinity here would end up being infinity over 2, which is infinity. So that's unbounded. So you have no horizontal asymptote there. Okay. Well, let's take a look at what if n is equal m plus 1. Now, I don't know if you remember this from Algebra 2 or pre-calc. If the degree of your numerator is 1 more than the degree of your denominator, then you have a slant asymptote. And you're a rock star if you remember that in order to find your slant asymptote, you would do long division and come up with the linear or the line from that. So even with a slant asymptote, that implies that the limit is plus or minus infinity. Okay, but we're not going to focus too much on the slant asymptote here. Okay? All right, so let's take a look at a couple of examples. Okay, so let's say we have a graph, and here we have some y equals L, and we have some graph that does that. So here the limit as x goes to positive infinity, so as x goes unbounded to positive infinity, your y values are going to be bounded by this horizontal line, y equals L. So the limit as x goes to infinity of f of x is equal L. By the way, no, I'll leave it like that. Okay, and another example, let's say we have this, and we have a graph that looks like this. Let's call this G. So we have a vertical line, x equals c. Then we can say the limit as x goes to c from the left, because it's approaching c from the left, of f of x is equal to infinity, positive infinity, because it's rising unbounded. Okay, so let's take a look at an example. What's the limit as x goes to infinity of 5 minus 2 divided by x squared? So remember, the limit of a plus or minus b is the limit of a plus or minus the limit of b. So this is the same thing as the limit as x goes to infinity of 5 minus the limit as x goes to infinity of 2 divided by x squared. And in this case, the limit as x goes to infinity of 5 is just 5, because this is a horizontal line at y equals 5. So you're going to get 5 minus, well, direct substitution here would put this at 2 over infinity. So a number over infinity is equal 0. So 5 minus 0 is equal 5. Okay. Let's take a look at another example. How about the limit as x goes to infinity of 2x minus 1 divided by x plus 1? Well, notice that the degree of your numerator, the highest degree in your numerator is 1, the highest degree in your denominator is 1. So the limit as x goes to positive or negative infinity of a rational expression where the degree of your numerator and the degree of your denominator are the same, that's just equal to the coefficients of that largest degree. So that's going to be the coefficient of x, 2x minus 1. The coefficient of the x here is 2. X plus 1, the coefficient of the x here is 1. And that answer is 2. Okay, another way to solve this problem would be to divide all of the powers, all of the terms, by the highest power in your denominator. So please write this down and highlight it. So you want to divide, if I could spell, all terms by the highest degree, or largest degree in the denominator. So it always has to be the largest degree in your denominator. In this case, x to the first power is our largest degree. So the way we would write that would be the limit as x goes to infinity. So it would be 2x over x minus 1 over x divided by x plus 1 over x. So that is the limit as x goes to infinity of 2 minus 1 over x divided by 1 plus 1 over x. So you'd end up with 2 minus 1 over infinity, 1 plus 1 over infinity, and 1 divided by infinity is 0, 0, so you end up with 2 over 1, and our answer there would be 2. The reason I like that second method is because you can apply that to problems that don't necessarily have x's or algebraic expressions. Okay, and we'll see some of those a little later on. All right, let's take a look at another example. Okay, how about the limit, as x goes to infinity? So this one is 2x plus 5 over 3x squared plus 1. Now, the degree in your denominator is larger than the degree in your numerator. So this answer should be 0. Because when we first started, we said if, here, we said if n is less than m, in other words, if the degree of your numerator is smaller than the degree of your denominator, then it's going to be 0. So let's see if we can solve this using the last method I talked about. So this would be the limit as x goes to infinity, the largest power in the denominator is x squared. So this would be 2x divided by x squared plus 5 over x squared all over 3x squared over x squared plus 1 over x squared. So that gives us 2 over x plus 5 over x squared divided by 3 plus 1 over x squared. Now, taking the limit as x goes to infinity, you're going to get 2 over infinity, that's 0. 5 over infinity, that's 0. So you're going to get 0 in the numerator, and you're going to get 3 on the bottom because 1 over infinity is 0. So 0 divided by 3 is, in fact, equal to 0. Okay. So how about next example? Limit as x goes to negative infinity, and then this one will be 2x squared plus 5 over 3x squared plus 1. So think of a graph. So now what you're thinking about is the limit as x goes to the left, to negative infinity, what's happening with your y values in this graph. So if we were able to graph this, we would be able to kind of determine. But here, the degree of your numerator and denominator are the same, so your answer should be, and it is, 2/3. But if we were to do it by this previous method, well, that would be the limit as x goes to negative infinity of 2x squared over x squared, 5 over x squared, divided by 3x squared over x squared, plus 1 over x squared. Okay, that one's equal to 0. It's equal to 0. X squared divided by x squared is 1. So we're going to end up with 2 divided by 3. Okay. All right, let's try another one. All right, what's the limit as x goes to infinity of 3x minus 2 over the square root of 2x squared plus 1? All right, now this one we really have to think about, because if we were to just do direct substitution, you are going to get infinity over infinity. But we also have to kind of figure out what's our highest power in our denominator. What's the highest power in our denominator? In other words, you have a radical square root and you have an x squared. What is the square root of x squared? Well, the square root of x squared is equal to x if x is greater than or equal to 0. The square root of x squared is equal to the opposite of x if x is less than 0. In this case, because your limit is x going to positive infinity, we know that our x values are greater than 0. So the square root of x squared would be x. So the highest power in our denominator is x to the first power. We're representing it as the square root of x squared. So this becomes the limit as x goes to infinity. Now, the numerator, 3x minus 2, I'm going to use the form of square root of x squared, that's x. So that'll be 3x over x minus 2. And our denominator, that's square root, I'm using the square root of x squared. So here that's 2x squared over x squared minus 1 over x squared. So that gives us 3 minus 2 over x, sorry, that was over x too, divided by the square root of 2 minus 1 over x squared. Now when we evaluate this and we take the limit as x goes to infinity, you're going to get 3 minus 2 over infinity, square root of 2 minus 1 over infinity. So that's 0, and that one's 0. So you're going to get 3 divided by square root of 2. And let's recall that 3 divided by square root of 2, we want to rationalize the denominator, multiply it by a special form of 1, and we get 3 square root of 2 divided by 2. So that would be our solution there. Now we're going to take a look at the same problem through a slightly different lens. Okay? So we looked at this problem as the limit as x goes to positive infinity. Now let's take a look at this problem as x goes to negative infinity. So same problem. So the limit as x goes to negative infinity of 3x minus 2 and the square root of 2x squared plus 1. Okay. Also keep in mind that the square root of a divided by b is the square root of a divided by the square root of b. Now here we already said that the square root of x squared is equal to x if x is greater than or equal to 0. It's the opposite of x if x is less than 0. So here, because we're taking the limit as x goes to negative infinity, our x values are less than 0. So what that means is that the square root of x squared is equal to the opposite of x, negative of x. Or, if I wanted to put the negative on the other side, that would be the negative of the square root of x squared is equal to x. Okay, so that's what we're going to use there. So now this becomes the limit as x goes to negative infinity of 3x over x minus 2 over x all over. Now here I have the negative of the square root of x squared, so I'm going to put the negative outside, and then that square root of 2x squared over x squared plus 1 over x squared. So that's 3 minus 2 over x all over the negative of the square root of 2 plus 1 over x squared. Now when we let our limit as x goes to negative infinity, we are going to end up with 3 over the negative square root of 2, or negative 3 square root of 2 over 2. Okay. So this is it for today's lesson. Your homework is lesson 1.6, page 115, numbers 1 through 6, and 13 through 32. All right, and I will see you guys later.